Good afternoon, and thank you for joining us on our call today to hear about the advantages that thermal imaging cameras provide over traditional spot IR thermometers. My name is Nicole Van Wert from Transcat, and I'll be your moderator this afternoon. Our presenter today is Ed Kohanek with FLIR Systems. Ed is the Eastern Regional Sales Director at FLIR. He has been working with customers on their thermal imaging camera needs for his over 14-year tenure at FLIR. He's a certified thermographer, having received his certification through FLIR's Infrared Training Center. More thermographers have been trained at FLIR's Infrared Training Center than at any other training organization in the world combined. Today we will spend the first part of our time in presentation, and we will end the call answering your questions. During any time of the presentation, you can send questions through the question box to the right in your webinar control. I also wanted to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Ed.
Good morning, good afternoon, Nicole. Thank you.
Thank you.
I'm just trying to see why.
We need to hide.
Just bear with me, everybody. My mouse has decided not to advance the slides. Hold on.
Ed, if you go down to the left-hand corner in the bottom of your slides, there will be, you'll hover over different arrows. Use that control.
All right, thank you.
Sure.
Good afternoon, everybody, again. My name is Ed Kohanek, and I work for FLIR Systems. This is my contact information as well. So if you have any questions or anything else, please reach out to Transcat too. I'm going to give a presentation that will discuss spot IR temperature guns versus thermal imaging cameras. I'd like to start off with a challenge. You are not doing everything you can to prevent unscheduled downtime. The good news is there is no better time than today to change that and get ahead of your facility issues that are about to happen. Every day you go to work, there's a chance that you will have your next electrical or mechanical breakdown. But how do you know what will break down next, or where will it break down? You have hundreds of targets to take care of, and it can be daunting if you're not prepared for it. As you can see by this picture, there are lots of applications that will fail throughout the day, and having no clue what's going to fail next will cause many problems. A lot of times there's clues. Sometimes your coworkers will tell you that they smell something burning, or you are getting nuisance trips, or you feel a vibration. The system is bad, broken, wrong, or you keep replacing the same components, that it's musty in here, it's too cold or too hot, or there's potentially a roof leak. So what are the consequences of this inaction? Every production line shutdown, every minute trying to diagnose a problem, every overtime request equals lost reputation and customers. Basically, you know, you're seeing the money go out the window or burning up. In the past, to get ahead of these problems, companies would hire more employees for maintenance. But today, that is hard to do as cost is very high to bring someone on. The return on investment would be very long for a new person when you factor in training, experience, vacations, sick days, etc. And also, as you know, it's very hard to find good quality people in the maintenance world. However, I have a suggestion. What if you could have the ability to predict the future yourself? If I gave you a tool that required minimal training, never took a sick day, was always there when you needed it, and could see things starting to fail before they did, that would be pretty cool, right? Well, that describes a thermal imager. Thermal imaging has been around a long time. The barrier has always been cost. 10 years ago, thermal cameras cost over $50,000. Even when we broke the $5,000 cost barrier a couple of years ago, it was still hard to justify. Well, the cost barrier is a thing of the past, and as you will see in the end of this presentation, that thermal imaging is more affordable today than ever, and you can get a camera for under $1,000. Did you know time was the most measured parameter in the world? I bet you don't have to look very far from where you are right now to find what time it is, whether it's on your watch, your computer, your smartphone, etc. There's a time clock somewhere, everywhere. Do you know what the second most measured parameter is? It's temperature. In fact, if you listen to the radio on the news reports in the morning, they always go time and temperature on the hour. So even the news radio recognizes how important temperature is to everybody who in everyday life. Temperature tells us so much about how things are working. Think of your body for a second. Our core body temperature is 98.6 degrees. If we get sick, we feel the onset of the sickness in our throat or our head or our lungs. As this happens, our body temperature starts to rise. Ironically, our equipment does the same exact thing. As it starts to break down, the temperature starts to rise to the point where it will fail. It's during this time period you have the chance to catch the problem before it fails. The current most affordable technology is the spot gun. The cost of this tool is anywhere from $50 up to $500 or even $1,000 for some of the more advanced ones with high temperature options. And companies such as yourself have been relying on this technology for years because it was the only affordable way to measure temperature when compared to a thermal imager. So how does it work? Both the spot gun and thermal imager work in the infrared part of the electromagnetic spectrum. As we can see from this chart, we use most of the electromagnetic spectrum every day. From X-rays to see our broken bones, to visible light that we are using to see this presentation, to microwaves to heat our food, even the old TV and radio signals that we use to watch TV and listen to the radio are part of the electromagnetic spectrum. However, right between visible and microwaves is IR. And the spot gun and thermal cameras are sensitive to this part of the spectrum. IR waves are emitted by all objects. Radiation increases with temperature. Mechanical items get warm because of friction. Electrical items because of resistance. You can detect moisture because of evaporation, and energy loss because of heat transfer. And in this graph, we clearly see that when you put your hand near the fire, you'll feel the radiation from the fire. The camera senses that same radiation and processes the signal. If you put your hand near ice, do you feel the radiation? No. But that radiation is there, as we had just said, that all objects emit infrared radiation. So whether the object is hot or cold, you're still able to get a very good picture. And there are a lot of instances where wanting to find something cold is as equal as and important as finding something that is hot. Now that we know temperature will give us a clue to something about to fail, let's see how the affordable technology in the spot gun has affected our ability to see it. In this section of the presentation, we will discuss the replacement of the inaccurate, inefficient, and ineffective technology. This tool bag represents the leap of the thermal camera from an instrument to a tool. We are going to discuss the hidden truth of spot guns and that a transition is occurring where customers are opting for a thermal imager. I've even had one customer tell me that these devices lie to you. And we're going to see why. Why the conversion to thermal imaging? Three main criteria: speed, accuracy, and documentation. And when you combine speed and accuracy, you get something very important. You get a much safer working environment. Whether it's human immediate safety from a dangerous situation, or the safe working environment caused by mold, a thermal camera can help detect the issues that create those situations as well. So let's see how the spot gun works. The spot gun has one detector and no image. In this example, you point the spot gun at the target and you get a temperature measurement. It's very simple and apparently very easy to use. On the other hand, the thermal camera has what is called a focal plane array. Depending on what type of array size you get in your camera, it could have 80 pixels by 60 pixels. This would be a 4800 pixel array. Other common array sizes are a 160 by 120, which is highlighted in this frame right here of the FLIR E6. That has 19,200 pixels. There are arrays that go up to 76,800 pixels, and even some larger arrays in the handheld cameras that go up to 307,000 pixels. Some of our scientists out there actually use thermal imaging cameras that have over 1 million pixels, but we are not here to discuss those cameras. The nice thing is, if you think about it, as in this picture, having a 160 by 120 array can conceivably be the equivalent of having 19,200 spot guns. This is obviously not something that would be considered practical, but it's absolutely the performance you can expect from a thermal imager. So let's look at speed. Let's see how speed is advantageous to a thermal imager. The faster you can find the problem, the more time you have for your other work. In this example, we see a set of 3 fuses. To find out if there's an issue, you have to measure this target 9 times at the 2 connections and the body of the fuse. As we can see by the yellow crosses, those are indicating how many times I would have to shoot this target to see if I actually have a hotspot. If you have many of these, you would have to measure this repeatedly, and this could get tedious and repetitious. On the other hand, if I look at it once with the thermal camera, I will clearly see that there is a problem with C-phase. The simplicity of thermal is quite evident. Which of these fuses doesn't belong? Once I can see that one is actually warmer or looks different than the other, I have the ability with the camera to measure any component on this that I wish. For example, the C-phase fuse is measuring at 106 degrees Fahrenheit, and the reference fuse in A-phase is measuring around 79 degrees. This is approximately a set 27-degree delta. And as we will see shortly, a 27-degree delta will lead us to a decision on when to fix this. Doing a basic comparison like this is sometimes as easy as it gets with thermal imaging. For example, if you were challenged to find the hot spot in this nest of wires with a spot gun, I think you'd have your hands full. Obviously, something like this, a thermal camera would far better perform in this situation. So let's talk about accuracy. If your instrument is giving bad readings, then you're not likely to trust it or actually use it. And as one customer told me yesterday, he had asked me if the instrument he's been using for the 8 years has been giving him wrong information. And unfortunately, I had to say yes. And it was no fault of his own. It was just the limitations of the instrument. If you look at your spot gun, all spot guns have spot size ratios. On the side of the gun is a graph that tells you what that is. In this example, we will look at a popular specification of 12:1. A 12:1 spot gun will accurately measure a 4-inch diameter target from 4 feet away. So 48 inches away, divide by 12 gets you a 4-inch diameter. When you think about that, a 4-inch diameter is a fairly large target. generally larger than most electrical targets that you would see in your environment. Another popular specification is 8-to-1. My customer yesterday was using an 8-to-1 spot gun. At 8-to-1, if you're 4 feet away, your target size is 6 inches. That is huge. That means for accurate temperature measurement, your target hotspot needs to be much larger than most of the equipment that you're measuring. Or you may have to move closer, which could increase the chance for an accident. Even if you move twice as close, if you were 2 feet away, your measurement size would be 3 inches, still larger than most of your electrical equipment. So let's look at this picture. Is this accurate? Is this acceptable? We have a hot fuse. B phase is clearly warmer than A and C. The spot gun tells me it's only 90 degrees. The measurement circle is much larger than the fuse clip. Therefore, the spot gun is averaging the colder areas around the hot spot to come up with a temperature far below accurate. So as we can see, the surrounding areas of 66 degrees, of 84 degrees, and of 145 degrees, those are all being averaged in that circle, and a spot gun is measuring 90 degrees. Let's look at that fuse again with the thermal camera. By overlaying the number of pixels on the target, I see that a lot of the pixels are small enough to encompass the target. And one of those pixels is able to highlight and measure accurately the temperature measurement of 145 degrees. In this example, we have a 50-degree temperature rise over what the spot gun said. That's pretty impressive. As you can see, the camera is indicating a much more severe problem than existed, and that will definitely affect your decision on when to fix the problem. Now, these targets are relatively close. You know, you're within 2 to 4 to 5 to 6 feet. What happens when you look at a utility pole that's at least 20 feet up in the air? Let's look at the consequence of a spot size on this target and estimate how large a diameter a spot gun would measure. By using a camera, I've digitally zoomed in on this target so we can see that the localized hot spot is around the bolts. And I can measure 173-degree temperature. If I use the spot gun, and I'm going to go with a more advanced spot gun, something that had 30-to-1 spot size ratio. That's a fairly expensive spot gun. At about 20 feet, the diameter of the measurement circle is 8 inches. If you hold your fingers apart by 8 inches, you'll see it's much larger than that target. And when something's very far away, it's very hard to get close to it. And as we can see in this picture, you are averaging a lot of the sky in the background, and the sky is measuring roughly at 32 degrees in this situation. So the sky is very cold relative to the hot spot. So your spot gun would be severely challenged in coming up with an accurate temperature measurement. If we were using a 12-to-1 spot gun, you would now be measuring a 20-inch diameter circle at 20 feet away. And an 8-to-1 spot gun would measure at 30 inches in diameter. These instruments would be rendered useless once targets are even further away. The only option is to get close, and due to safety reasons or not having a bucket truck, that may not be the case. And if you look through your facility, there are many applications that are up in the ceiling, far away, hard to reach. And a thermal camera gives you the ability to find problems at a safe working distance. So let's talk about safety. Many times working in confined spaces is a cause for concern, especially when there's energized equipment or moving parts. As a fall with the speed of a maintenance person can quickly scan and look for any temperatures well above ambient. Thermal cameras even have tools such as isotherms that give you the ability to find unusually hot areas quickly. By finding these hot spots, existence means that you can now adjust your work to solve the problem before putting your life or your workers' lives at stake. For example, in this example of a termination, the camera found a hot spot greater than 1,075 degrees. We are near the limits of what this camera can measure, as indicated by the greater sign on this picture. A nice tool on most IR cameras is the area box. By putting the area box on the target, the camera will tell you the max temperature inside of it. The tool relieves the pressure of putting the spot directly over the hot spot and thereby masking it for visual purposes. If I were to have used a spot gun in this situation, this would have been the approximate size and average that that spot gun would have measured. What would have been the temperature measurement then? The temperature could have easily dropped over 500 degrees. Now, you still would find a hot spot. I'm not saying you would not have. Now the spot gun would have still found the problem, but you would have had false sense of security. You may have thought that this problem was only 600 degrees. The problem here is the melt point of aluminum is around 1,220 degrees. And since the camera is already telling us we're above 1,076, we are very close to the melt point. Would you want to be in the area if the termination melted down while you are investigating it? If you're using a spot gun, you certainly would have put yourself at risk. By going through training, you would have learned to freeze and leave. Freeze the image, take a quick measurement, and leave the areas so in case something happens, you're not around. This is a clear way of how a thermal imager can help save lives. On this two-pole breaker, we find another problem. The target is measuring 220 degrees. That is fairly hot. However, there's another concern. According to the data taken, the load is fairly low. Load or amps on a target have a direct effect on temperature measurement too. So it's necessary to measure the load of every electrical application when possible. If the load reaches normal, then you can expect a far different temperature reading. If the load doubles to normal, the temp rise is exponential because power equals IR squared, where I is for current is increased when it's multiplied by the resistance, which is squared. Conceivably, the temperature can increase by 4 times. What would you have done if that breaker measured 600 degrees instead of 220 degrees? What was if the load was even 4 times larger than what would have happened? By using a thermal camera, you can find these problems and solve them before they explode. Again, I'll use the white circle to show approximately what that average would have been, the size that you would have measured with a spot gun. The chances of you missing this problem or missing the severity of the problem increases by using a technology that it is not equipped for. Every time I hear about a facility that had a fire and they traced it to an electrical problem, I always say to myself, it didn't have to happen. So let's look at how the spot gun versus the camera collects information. There is a dramatic difference here too. With the spot gun, basically all the recording, all the data is on your shoulders. You have to write everything down and keep very good notes that everyone else will need to read or understand. With the thermal camera, however, you're able to take a thermal image and a visual image all in one click. Thermal cameras also come with software that allow you to create reports based on the images you took. You're also able to analyze the images by changing the color or the contrast and measuring more spots on the image. Basically, the images are live and active in the software after you are back in the office making the determination how to correct the problem. Finally, and most importantly, people believe with their eyes and not their ears. By creating an image or a report, you're able to create a convincing story on why the problem exists and how to correct it. It's hard to tell someone no when presented with the visual facts. Now, I would like to say full disclosure here. I work for a manufacturer of both thermal cameras and spot guns. So I'm not here picking on the spot gun. I'm just suggesting that there are better alternatives out there. You now have seen why thermal cameras are far more useful than a spot gun. We have shown by speed, accuracy, and documentation, your thermal cameras will provide a faster return on investment and create a much safer work environment. So now we're going to talk about some typical indoor electrical applications and some building applications. If you want to see some outdoor electrical or mechanical targets, you can go to the Transcat webpage and see my webinar on those targets as well. That webinar was called Thermal Imaging Camera Applications in the Utility and Energy Industries. It was recorded back on August 6th, and I went through a number of outdoor electrical applications and a significant number of mechanical applications, from motors to gearboxes to bearings. When discussing indoor and talking to electrical contractors or maintenance people, I get one question every single time. How hot is too hot? And in the past, and as I'm doing now, I provide a chart. This is called the NETA guide that is provided to you when you attend Level 1 training through the Infra Training Center. NETA is the International Electrical Testing Association. They came up with these guidelines. And since they represent electrical contractors, they're going to be very conservative with temperature, meaning if there is a slight temperature change, they're going to have a call to action that you should take care of it sooner than later. Notice that this table has two columns. One is for delta T on similar components, and the other is for delta T on components versus ambient air. I want to make one thing clear. This is assuming that you have similar loading through the system. When I say delta T, the delta T means difference. These are derived from the camera, from the spot meters in the camera or in the software. If we look at the difference in rise on similar components, any temperature from 2 to 5 degrees represents a possible deficiency. From 5 to 27 degrees indicates a probable deficiency. And anything above 27 degrees represents a major discrepancy, repair immediately. As I said, this is somewhat conservative in the temperature rise. If you're comparing delta T's between ambient air and the target, you'll see that the spectrum is a little larger. So you have up to 18 degrees for possible deficiency, up to 36 degrees for a probable deficiency, up to 72 degrees to monitor it, daily, and anything greater than 72 degrees should be repaired immediately. So here's an example of applied temperature criteria. Please note that the temperature is a delta of 46 degrees over ambient. The 87 degrees Fahrenheit is the air temperature. Referencing the NETA table as shown previously, this is a monitor until corrective measures can be accomplished. Again, load has to be similar. You will see that terminations are a tremendous source point for loose connections or faulty components, and this is generally where you find a lot of your issues. Here's an example of a fusible disconnect, and it's clearly having a heating on the end of the phase C load and fuse barrel and clip. We can see that it's measuring 250 degrees Fahrenheit versus a reference of 135. The nice thing is the problem in the box connector or in the spring tension of the clip? With thermal, the picture tells you what you need to know, something a spot gun cannot do by just giving a temperature measurement value. Definitively, it is a clip problem, as the majority of the heat is in the right area of the fuse end. Fuses that are heated have lost some of their ability to trip at the proper current. The heating causes the fuse aging process to accelerate, and also the clip should replace completely due to the heating as well. A lot of times when you see very hot targets, sometimes that temperature is exceeded past where that metal has reached its fatigue strength and has softened that metal up. By simply just tightening down, you may come back in 3 to 6 months and find that problem has recurred itself, where a full disassemble and replacement should have happened. A very common multi-conductor mechanical tap connection is our next example. The insulation covering this makes it an indirect for internal temperature measurement, meaning I cannot see the splice inside. But the comparison to another similar splice and the actual current passing through this joint indicates that this should be repaired at first opportunity. One of the decision-making criteria with this component is that this is a main power splice to a production machine. This certainly makes this a high priority to repair. If you lose this splice, you lose production. And in previous seminars, by losing production, the cost for business interruption far exceeds any cost of any thermal camera out on the market today. In this conductor and termination, improper tightening, sometimes referred to torque, is quite common. Reliance on just tightening is a false guidance. The connection needs to be cleaned and prepared properly for the connection to maintain low resistance. One of the other problems that can be found is improper bolts being used. If the connections are to remain tight, the manufacturer will recommend a specific bolt type. Example, if stainless steel bolts are specified and carbon steel bolts are used, then the connections will experience torque-related issues. There are plenty of opportunities, and during commissioning periods after installation, a thermal imaging becomes very useful to make certain all the proper tools were used and everything was properly tightened down. For any piece of equipment, it's only as strong as its weakest link. The weakest link in this example is a $2 fuse. Do you want to be in the position of not discovering this problem exists because you didn't have the technology to find it fast, measure it accurately, and document the problem? And that's where thermal imaging really helps out. When you use it, it provides that instant feedback. You find the problems. You'll use the camera more often. With the spot gun, as we saw by its challenges, the chances that you are finding a problem have diminished greatly, and to measure it accurately has gone down. So relying on that technology becomes less and less. By having the camera and utilizing it, common small problems like this can be easily found, and it is encouraged to use. Here's a circuit breaker of a picture that I actually took 12 years ago. Here, C phase is clearly warmer than A or B by 24 degrees. What's interesting was this was the first thermal camera that incorporated a visual light camera together in one package. Today, that is commonplace. But for this pharmaceutical manufacturer to utilize this technology to find this problem and to document it was something that they were actively looking for. A lot of these applications challenge spot guns based on distance, how far away they are. and actually the subtle temperature differences that they give off. When you're talking about bus bars, or in this case, bus bar fusible disconnect, note that the temperature of the switch enclosure is higher than the background by about 7 degrees. We can clearly see that on the image, as we can see the box being yellow versus the outer casing being a purplish color. By seeing that, gives you indication visually that something is going on. I would challenge, if you were measuring something and it was only a 2-degree rise based on the spot gun, that would be hard to understand what was actually happening. So we see that we have a 7-degree rise, and this is an indirect heating, as inside the enclosure, something inside is warm enough to warm the exterior. Note it also has enough energy to conduct down the bus bars in each direction. Why am I talking about this problem? Because it can be quite serious. There is no active heating component inside the cabinet. All the heat we see is from passive connections that have become high-resistant heat sources. Think of those heat sources inside this acting like a hairdryer blowing onto the side of the door that you are seeing. When this was opened up and looked inside, it was found that the internal components had temperatures over 350 degrees, and the insulation was burnt and charred. Again, these are reasons why factories, facilities, hotels call the fire department, and I say to myself, it didn't have to happen. Another common item is bus ducts. We can see the temperature rise is 16 degrees from the normal part of the bus duct to the obvious hot spot. And as we know with indirect temperature measurement, you can multiply the temperature delta, in this case it's 16 degrees, by 25 times. So the actual delta, if we were to take the covers off, would be well over 400 degrees. And as we know, when a bus duct fails, it can explode, creating a very dangerous environment if anyone was near it. Here we see battery cells and connection components. UPS systems are plentiful these days, and they're helping industries eliminate downtime or even blips in energy blackouts. This is a cell experiencing a breakdown internally. The battery is under a maintenance charge of fairly low amperage. Generally, the measurement of temperature is unnecessary, as really all we're looking for is to see is a temperature delta of one battery cell to the other. One expects never to see this contrast in a battery bank, but general warming is normal, but not one cell should contrast the others. The fact that you can see this means that there's a chemical reaction going on in that one cell. One would not want to experience the same resistance under full current discharge, as this tends to get substantially hotter and proposes a component destruction issue. So when you're looking at batteries, be aware of the dangerous situation that you are looking at if you see a hot spot. And here we see a hot spot at the connection of about 120 degrees. The hot spot, it measures 201, where the cable measures 80. So we have a 120-degree rise. If there was a call for power from this, that hotspot would increase dramatically, and I certainly would not want to be in that environment if something were to go wrong. And as you can see by the size of the battery, the angle that you're looking at it, a spot gun would have a really difficult time indicating that there was a problem in the first place. Here's an unusual application that I was talking to an electrical contractor a couple of days ago with. I found it very interesting. A lot of companies use thermal imaging to see subfloor heating. Generally, why? Because if they're putting furniture in place or in the kitchen or the bathroom, they need to bolt down something. They get to see the pattern and see where to drill the holes. But more importantly, this contractor had a unique solution. He would lay down the subfloor heating. He'd take a picture of it to make certain that he did it correctly. And then when the tile guy came and laid down the tile, there was a chance that the tile guy could have screwed up his system. And then once the system was in place and the nice tile was put down, the customer may complain that the subfloor heating is not doing its job. This electrical contractor had proof that when he had left the job, the subfloor heating was done correctly and was put in as specified. It was this way. It was therefore the responsibility of the tile person to come in and repair it. So thermal imaging can also document when a job was done correctly, as we can see in this situation. Now we're going to talk a bit about some building energy and moisture images. We're not going to spend too much time on this, but there are some really simple, easy to use applications for the thermal imager. This is one of my favorite pictures that I took many years ago. A customer had a factory. He had an office in the factory. And they did not heat or cool the factory, so in the summer or winter, his office was either hot or cold. He contracted for an insulation company to come in and install insulation blown in his office. What you see is the results of the job. The customer was unaware, but his contractor did blown-in insulation every other stud bay. So where you see the cold purple areas, that is indicating where there is missing insulation. The customer was completely unaware that he had been ripped off. The camera clearly shows a predictable pattern across the 3 walls that faced out into his factory. Here's another example. This one was not done because they were getting ripped off. It was just what happens sometimes with blown insulation. It doesn't fill all the voids. And we can clearly see the areas that are dark purple are where there's missing insulation. It is colder outside, so where there is insulation, it looks yellow, and where there's missing insulation, it's purple, and that's where excessive heat transfer is happening. Argon is used as an insulation gas to increase the R value of windows. If argon leaks out, you'll see a predictable pattern caused by convection inside the windows. In this case, the windows have lost all its insulation values at this point. We can clearly see that the 3 lower windows have the circulation pattern where it has lost its argon. And I'm sure the people who are in that building near those windows probably feel colder than some of their counterparts elsewhere in that building. Probably the easiest application for thermal imaging is the detection of moisture. Due to evaporation, water can be easily discovered on most applications and most building materials. As we can see here, water looks cold to the camera on the sheetrock. While an IR camera cannot discover mold, it certainly can discover moisture, which can lead to mold in an unhealthy work environment. So whether it's rugs, sheetrock, building materials such as wood, they all absorb water, and as water transitions from a liquid to a vapor, it's evaporating, it's colder than the environment, and you will clearly see it with the thermal camera. Finally, our last application is roof moisture detection. Water can be discovered in the layers of insulation under the roof membrane. You need to scan the roof just after sundown when the roof has heated up due to the sun's solar radiation. So depending on where you are today, if there is a clear sky and the sun is heating the roof to a nice warm temperature, all you have to do is wait for evening. As soon as the sun goes down past the horizon, The dry roof cools rapidly due to heat transfer based on the roof facing a cold sky. The wet roof, the water underneath the membrane, will retain the heat. And as we can see in this picture, it looks like a hot spot. You have now found your roof problem. You've chalked it out, as you can see on this image, where the repair needs to be. And you can avoid the costly repair that roof construction companies want by replacing the whole roof. All you have to do is replace the wet roof. So this ends the technical portion of the webinar. I'll briefly discuss what devices are available in the thermal camera line. I will not go into depth or too much time. At the end of this presentation, you can reach out to Transcat for more assistance and if you are looking for a demonstration. At FLIR, we have 3 model classes that you can choose from. But the most important thing you need to do is ask yourself some basic questions. For example, how far from the target am I? How hot is the target? Thermal cameras can measure up to 2,000 degrees C in some cases and 3,700 degrees Fahrenheit. What are some of the other applications? I had mentioned outdoor electrical. I mentioned mechanical items. Maybe research and development applications where targets are very small. How often will you use the camera? Is it an instrument or is it a tool? What other features do you need from the camera? Will the camera be used by technicians, engineers, research and development professionals? And what type of reporting or trending will you do? All goes into figuring out what is the most appropriate system for you. Our first class, and briefly, is the new FLIR EX series. It's a point-and-shoot camera, and it's our spot gun replacement camera. Some of the key points of this camera: it has a radiometric JPEG image storage, meaning images are stored in a common file format we are all used to in the visible world. It has FLIR's unique MSX technology, and I'll talk briefly about that in the next slide. It's focus-free, has a fairly large 3-inch color LCD, measures accurately up to 482 degrees Fahrenheit, and has a cost starting at $995 for the E4 and goes up to $595 for the E8. So what is MSX? MSX stands for multispectral imaging. FLIR introduced this technology 3 years ago in our FLIR T640 camera line. Here's a high-definition picture without MSX. By augmenting the thermal image, we can now see the details of the visible light in the infrared spectrum. If I go back, I see that there is A phases warmer than B and C, but I don't know what the identifications are. By using MSX, I can now identify that the hot elbow is H1A, and the reference elbows are H2A or H3A. Well, MSX is now on every thermal camera we make. And let's see how it applies and helps out on a very basic thermal image. This is an image from the E4, and the E4 has 80 by 60 pixels or 4,800 pixels. This is a fused panel that does not have a lot of warming on it. Yet I can see the beginnings of a thermal source. With MSX, I am now able to augment the image to see that it is fuse 15 that is starting to get warmer than all the other fuses. And this is where MSX makes thermal imaging easier to use, easier to understand. Moving on to the next E-Series platform is the EXX. And this offers a larger touchscreen, Wi-Fi and Bluetooth for remote reporting. It also has MSX technology. It has a laser pointer a video light to enhance the visual image. You can add accessory lenses, whether they're wide angle or telephoto, and has temp ranges up to 650 degrees C. The cost for this camera class is from $4,000 to $8,000. And lastly, we have the High Performance T product line with ergonomic outdoor design. These cameras, some of them have an eyepiece on it that makes working outdoors very easy. High temperature up to 2,000 degrees C. High resolution up to 307,000 pixels. And remote control functionality with an iPhone or an Android device. General pricing is from about $8,500 to about $26,000 in this camera class. So that ends this presentation on thermal imaging and replacing spot guns as your tool of choice for diagnosing pending problems within your facility. I'm going to turn the webinar back over to Nicole and see if we have any questions.
Thank you, Ed. All right, so we're going to move on to the question and answer portion of the presentation. So the first question. Oh, and as a reminder, if you'd like to ask a question, please send it through the question box in your webinar controls. It should be on the right side. So the first question, can you measure a target 40 feet away?
Yes. All cameras have a variety of ways of doing it. Depending on the size of the target, if the target is fairly large, your camera, depending on its number of pixels, whether it's a 160 by 120 or 320 by 240 or 640 by 480, will have varying degrees of measuring it accurately. We also can apply telephoto lenses, whether it's a 2x telephoto lens or a 3x telephoto lens. You'll be able to dial in that target and get as many measurement pixels on it as necessary. So yes, targets that are far away can be measured easily with the thermal camera. It just depends on how many pixels we can put on that target.
Okay, thank you. I'll move on to the next question. Is software included for free?
Yes, thermal cameras have now come with software that allows for report generation. That is included free with the purchase, and it helps you as the thermographer to, not only find your problem, but document it, report it, and help get it fixed as soon as possible.
Okay, and just as a reminder, if you'd like to ask a question, we have a few more minutes. Please send it through the question box in your webinar controls. Okay, see this one. Can IR imaging cameras be used to distinguish air currents of different temperatures within an environment?
That's a great question, and unfortunately, I don't believe they can. Air does not have any emissivity capability. Air is not a solid. It's vapor, and I cannot see air temperature without it being on a target. If you were to put a target in the view of air current on one section and then another target that would have a different air current, I would be able to measure that target representing what air current it is in. But no, I could not measure air current with the thermal camera, unfortunately.
Okay. Okay, next question. Where can I get certified training?
Through Transcat. They offer the FLIR ITC, which is called the Infrared Training Center. The Infrared Training Center has level 1 through level 3 types of certification. This will give you the ability to understand the physics of infrared, to make accurate temperature measurements, and to create the best image possible with your camera that tells what may be happening with your target. So Transcat can, contact Nicole or your salesperson at Transcat and ask for the ITC Level 1 certification training program. We train all across the country, so depending on where you are, you may have a training class near you. Generally, we have 4 to 5 Level 1s every single month, somewhere local to where you are.
Okay, great. We'll move on to the next question. Are the units sent out with calibration paperwork?
Absolutely. All cameras are calibrated to NIST standards, and so when we build the camera, we look at a black body, we measure the black body with the camera, and we put a certificate that says when the camera measured that black body and it measured it accurately, and it comes with your camera. Yes. What I also forgot to mention about the training, and let me double back to that for a quick second, infrared training is non-denominational. What I mean by that is it doesn't matter whose brand of thermal camera you have. Training is all about the physics of infrared. So whether it's manufacturer A or B, the physics are all the same, even for a spot gun. The physics are no different. So you can be comfortable going to the ITC, the Infrared Training Center, for your training needs. Thank you, Nicole, let me jump back in on that.
Sure, and I will mention that at Transcat we do have a salesperson that is a Level 1 certified thermographer. So if anyone has technical needs, they can help you select the right camera for your needs.
Excellent.
Okay, so let's move on to the next question. How hot can you measure a target?
That's a great question. Every camera has a certain range to it. As we saw, the basic camera can only go up to about 500 degrees Fahrenheit, but we make cameras that will go up to 3,700 degrees Fahrenheit. Now, cameras don't measure that all in one range, meaning I could not measure a 78-degree temperature target and a 2,000 degree Fahrenheit target in the same range. Cameras have selectable ranges that you need to put the camera in to get the camera to measure accurately in that range. Generally, cameras will tell you when you're above the certain range. As we had seen in one of the pictures previous, the target was above 1,000 degrees, 1,076 degrees. That camera was telling you at that moment something was hotter than it could see, and if you had the capabilities in that camera, you could have adjusted it to the higher range and dialed in a more accurate temperature measurement after that fact. So real quick, you can measure targets up to 3,700 degrees Fahrenheit.
Thank you. Okay, our final question. Can I get a demonstration?
Yes. On the screen is Nicole Van Wert's email address and the Transcat phone number. Call her. She'll be happy to come out. No, I'm sure.
I think we'll work that out with you, Ed.
Yes. Well, call Transcat. Let them know you'd like a demonstration, and they will be in touch with one of us at FLIR, where we can arrange to have one of our team come out and show you how to use the camera and how to apply the technology for your needs.
Great. Okay, and we're actually right on time. So that concludes our time for today. If you have further questions or would like to find out more about Transcat's products and service offerings, you can contact us at 800-828-1470, on the web at transcat.com, or you can email me directly, as Ed said, at nvanwert@transcat.com. Thank you for joining us today, everyone. We hope you found the information useful and applicable to your processes and jobs. Have a great week.